In this problem, we're going to take a look at the rate of change and how to make a larger chart based on more values of the rate of change. And then we're also going to graph the original data and the rate of change and do an analysis of the graph using terms like minimums, maximums, increasing and decreasing. So one thing that I'll mention in this is that you probably are going to want to take some time and pause the video and complete what's going on your own paper as I go. All right, so let's take a look at what the problem is asking. The following data is a data set corresponding to the times achieved every 10 meters by Carl Lewis on the 100-meter final of the World Championship in Rome in 1987. So these values are given to you, and you're going to graph them here. And then for each successive time interval, calculate the average rate of change of the distance, and then what is a common name for the average rate of change of the distance? Well, the common name for the average rate of change of distance is velocity. Okay, and velocity is a measurement of the input and output of position. And the way that units work for all rate of change, not just this problem, is it's the output per the input. So the output is meters. Use this line for per, and then the input is seconds. So remember, output per input, so meters per second. So what you're going to do is to figure this out, you're going to use the rate of change equation, right? The rate of change equation is f of b minus f of a over b minus a. And you're going to do that in here. Maybe you can do this box, or you can use scratch paper. And so remember, this would be f of b, this would be f of a. So it would be 10 minus 0, f of b minus f of a, over the time that this was made by, or 1.94, the input of 10 minus 0, and then you're going to use a calculator and figure out what all those values are all the way across like that. The next one would be 20 minus 10 over 2.96 minus 1.94. So I went ahead and pre-did a lot of this problem, as you can see here. And so what I'm going to do is I'm going to ask you to figure out this chart. Let me zoom in on it. Exactly like I said, you're going to take 10 minus 0 and 1.94 minus 0 and simplify that on a calculator, and then 20 minus 10, and then 2.96 minus 1.94, and then simplify that on a calculator. All the numerators are 10, if that will help you. And then you're going to, from there, you're going to take the time and make a graph. So again, I would pause the video and graph the position here. Position is going from 0 to 100. There are 10 dashes, so I went by tens. And the time on the horizontal axis, he ran the race in 9.93 seconds, so I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did the same thing for the velocity of 1, 2. The time is always the same. So go ahead and make that graph. Once you do that, you're going to want to pause and make this graph. Notice the time again is the same, but the velocity I only went up to 12 because his largest velocity is 11.65. So I just went by twos, and then I took these values here and I graphed them as the output. But the input I just did by averaging these two numbers. You can eyeball it between 0 and 1.94, just kind of in the middle, or you can literally add these together and divide by 2. So go ahead and do that now too. So once you've made both graphs, the analysis of graph problems are fairly easy, and it's really interesting why this chart is so important for some of the preceding questions. So identify the increasing and decreasing consecutive intervals for position. Well, if you look at this graph for position, he is always increasing his position. And remember, he's running a race, so from 0 to 9.93, he is increasing his position. And you might wonder, well, why do we have a parentheses and then a bracket? Well, at the beginning of the race, before the gun goes off, the starter gun to go off, he is not increasing, so I do not have a bracket there. But at the end of the race, he is still moving forward, so I bracketed it. Okay, so where is he decreasing? None or does not exist. The AP and standardized testing do allow D and E for does not exist. You can't say nowhere or nothing. So none or does not exist. He's never decreasing his position. So identify the relative and absolute minimums for his position. Again, we're still talking about this graph. So his smallest position was at the very beginning, he was at 0 meters, and at the very end, he was at 100. So as a point, that point is 0, 0 as the relative minimum. It's the only minimum on the graph, and his absolute minimum is also that value. His absolute maximum was 9.93 in 100 meters. He ran a 100-meter dash, so that's his relative and absolute maximum. Again, this is a lot easier if you've made the graphs and done the chart, so you want to make sure that you pause and go back and do that if you have not done it yet. So when was, the next question, when was the velocity positive? So looking at the graph, you can see his graph is always positive because it's above the horizontal axis right here. As long as it's above this value, it's positive. So the velocity is always positive. Now, why is that so important? You'll see in a minute, because he clearly, if you look at this graph, he's not always doing the same thing, and that's another concept we'll talk about in the next problem. But in terms of his velocity, his velocity is positive from 0 to 9.93. And another way of thinking about that is he's always moving forward. Velocity has direction. So if your velocity is positive, it means you're simply moving forward. So when is his velocity negative? His velocity is negative, none or does not exist, because that would mean that he turned around in the race and was going backwards, and that does not happen. So now here's where we get to these curvy aspects of the graph. When were the velocity's rate increasing or decreasing? Okay, this is known as acceleration or deceleration. And what time interval was he decelerating or accelerating on? So when you look at the graph, it's a little hard to tell, but if you go back and look at the actual numbers, you can clearly see that starting from here, his rate is going up, right? So 5 and then 9, wow, he sped up there. He did it here. He did it here, meaning this value is bigger than this one. This one's bigger than this one. And again, he still did it here, but then all of a sudden here, he's kind of flat. Notice he's just sort of cruising right here. These are flat. He's not really going up. And then he goes up a little bit more right here. Boom, between here and here, he's going up again. And then here, he actually decelerates right there. And you can see that in the graph. That little is right there. And you can even see in the graph right here that he has now gone up. And you can even see the flatness in these values here. So that's why this rate of change chart is so important to look at with this graph. So you can see that his acceleration is, his velocity is going up here, creating acceleration, then he's flat, and then he goes up a little more. So from here to here, I'm just going to use the times above, right? So from 0 until this last value here, from 0 until 5.64, he was increasing his velocity or accelerating. He also does it a little bit right here. So those values, if you go back up and look at the chart, are between 8.22 and 9.07. And then at the very end, he's decreasing. So from here to here, he's decreasing. Okay, and so what it would be called in the middle is constant velocity. So the next thing is, during a sprint, why should his acceleration never be negative? Well, you are told as a sprinter to just run as fast as you can the whole time. In order to have your race have a constant acceleration. You want your acceleration the entire time to be positive. Okay, where did Carl Lewis attain his maximum velocity? So I can look at that in the velocity. It looks like his maximum velocity occurred right here. So you could say between 8.22 and 9.07. So where did he attain his maximum velocity between 8.22 and 9.07? Some runners are running their fastest as they cross the finish line. Does this appear to be true in this case? No, he's actually slowing down. This could have happened because he knew he had won, or his muscles could have just given out. So sometimes, you're told to be running as fast as you can as you pass the finish line, but sometimes, you might just get a little bit confident, or maybe your muscles have given out. So does this running style make sense for a long distance runner? Why or why not? And the answer is no, not really. Because a long distance runner needs to start out fast to kind of get position amongst all the runners, because there's not only 6, there could be 600 people in the race. And then you keep a consistent velocity, and then you speed up at the end. So it's not a run as fast as you can the whole time. It's more of a run as fast as you can, kind of keep consistent and then at the end, and that sometimes is called a kick. All right, I hope you've enjoyed these videos about applications of functions, and thank you for watching.